In the ever-evolving landscape of mobile AI applications, developers often face a crucial decision: which model to use for their needs. Specifically, when should we opt for Inception V3 or MobileNet retrained models on mobile devices? In this discussion, we're going to explore the performance comparison between these two models, dive into their strengths and weaknesses, and provide some real-world coding examples. This will help you make informed decisions regarding your mobile AI projects. So far, we've learned about the retraining process of MobileNet models, focusing on their lightweight architecture and efficiency for mobile applications. We've gone through setting up the environment, selecting model configurations, and executing retraining with the retrain.py script in TensorFlow. We've also covered the importance of testing those retrained models using the label image utility. And let's not forget, we discussed the performance advantages of MobileNet compared to traditional models like Inception V3. Now, here's where it gets really interesting. We'll delve into a comparative study of Inception V3 and MobileNet models, looking closely at performance, accuracy, and efficiency. Let's get started. To start with, let's dive into how these two models stack up against each other. So, Inception V3, this is a widely used deep learning model, right? It's known for its high accuracy, but here's the catch: it comes with a hefty computational price. Now, when we compare that to MobileNet, which was specifically designed for mobile and edge devices, we see that Inception V3 requires a lot more processing power and memory. If your application really prioritizes high accuracy, especially in tasks like image classification, then Inception V3 might be your go-to model. But be prepared for some longer inference times and a more substantial memory footprint. Just to give you some context, Inception V3 needs around 11.42 billion floating point operations, or flops, to perform a single inference. For a smartphone like the iPhone 6, which can handle about 2 billion flops, that means running this model could take around 5 to 6 seconds. And let's be honest, that's not optimal for mobile users, right? On the flip side, we have MobileNet. This one is all about efficiency. It strikes a balance between speed and accuracy. With its lightweight architecture, MobileNet significantly reduces computation without losing too much accuracy. For instance, during benchmark tests, a typical MobileNet model only requires about 1.14 billion flops to do an inference. That results in inference times that are roughly 10 times faster than what you'd get from Inception V3. So, there you have it, two models with very different strengths depending on what you'll prioritize in your application. Now, let's take a look at how we can retrain a MobileNet model for image classification using TensorFlow. First, we kick off the retraining process by running a command that points to the retrain script included in the TensorFlow examples. Now, here's something important. The underscore output graph parameter defines where the newly trained model will be saved. This is super convenient because we can easily use it later for inference. For our example, we'll store the model as dog underscore retrained underscore MobileNet 10224.pb. Next up, we have the underscore output labels parameter, which saves the corresponding labels for our retrained model. This step is crucial for understanding the classifications that our model will deliver. Now, let's move to the underscore imagedir parameter. This tells the retraining script where to find the images we're using for training. It's really important to make sure that these images are relevant to the classes we want to identify. Don't overlook this part. Next, we include the underscore bottleneckdir parameter, which is the location for storing the bottleneck feature data. And trust me, this helps speed up the retraining process significantly. Lastly, we use the underscore architecture flag to choose the specific MobileNet configuration. In this example, we opted for MobileNet 1.0.224. This architecture is lightweight and optimized for mobile use, which makes it an ideal choice for efficient deployment. Whew, there you have it, a comprehensive overview of retraining a MobileNet model. Now, let's dive into testing the performance of our retrained MobileNet model using the label image utility. This utility is crucial for validating how well our model performs on images it hasn't seen before. We'll run a command that outlines the location of our trained model graph, the input image, and the necessary processing parameters. So, the command begins with the path to the label image executable, followed by the flag -graph, which points to the retrained MobileNet model file we generated earlier. Then, we specify the image we want to classify using the -image flag, ensuring we pass in the image located at tmp lab1.jpg. Now, it's important to define the -input layer and -output layer flags, which tell the model where to look for input and where to output the classification results. We also include flags for image size specifications, like -input height and -input width, both set to 224 pixels, matching the input shape our model expects. Additionally, by setting -input mean and -input stand, we adjust the image normalization to align with the pre-processing applied during training. When we execute this command, it will return classification probabilities for the specified classes, allowing us to assess how effectively our model is doing. For instance, the output could indicate a high probability for the correctly identified class, which is definitely what we want to see. Now, let's implement the following command to create a quantized version of our mobile model. This command launches the retraining process, specifying that we want to generate a quantized model. You'll see this indicated by adding _quantized to the architecture parameter. What we're doing here is optimizing the model for mobile deployment, which is super important for devices with limited computational resources. Now, the -output graph parameter tells us where to save the retrained model. In this case, it'll save as dog retrained MobileNet 10224 quantized. Similarly, the -output labels parameter specifies the file path for saving the labels associated with our retrained model. This is crucial for understanding the outputs of the model, right? We also need to define the image directory and bottleneck directory where our training images will be stored and where the bottleneck features will be saved, respectively. Together, these parameters ensure that the retraining process aligns with the data we have. This quantization makes the model smaller and faster, which not only enhances performance, but also maintains a decent level of accuracy, making it really well suited for mobile applications. In conclusion, choosing between Inception V3 and MobileNet ultimately revolves around your project needs. If your primary focus is accuracy and you have the resources to handle those high computational models, then Inception V3 serves you well. However, if you're looking for a responsive and efficient model that works well within the constraints of mobile hardware, then MobileNet is definitely your best bet. So far, we've covered the basics of performance between Inception V3 and MobileNet, illustrating these points through retraining processes, benchmark testing, and the impact of quantization. Moving forward, we will delve deeper into real-world applications, discuss additional optimizations, and, address some common pitfalls that developers face when deploying these models on mobile devices. Thank you for joining me, and let's keep exploring the fascinating world of mobile AI.